Hello everyone, welcome to another episode of Easy Chemistry. In today's class, we are discussing about significant figures. Significant figures are meaningful digits which are known with certainty. Let's consider a real life example like we are going to shop to get some fruits like apples or mangoes. We are collecting some apples and keeping on the balance. We are about to buy 2 kilograms and we can see in the balance like 2.23 grams. Yeah, we'll round off it as 2 kilogram and we'll round off it as 2 kilogram, right? We don't consider much about that 0.23 grams. But when it comes to the chemistry laboratory experiments, there are different kind of experiments like quantitative, qualitative and all. In quantitative experiments, we are asked to measure the quantity. We have to find how much amount of the substance is present. So in that scenario, we will be taking the chemicals which will be in very less amount and keeping on the chemical balance. There are two types of chemical balance, the analytical balance and the digital balance. Now in most of the chemistry labs, there are digital balance. So we will be keeping the chemicals which are in less amount on a digital balance and we will check the weight. In that case, that 1.23 grams, that 0.23 and all matters. If the result is like 1.23 or 1.24, that 0.24 or 0.23, whatever the number is, it matters. So while doing the experimental measurement, there will be some amount of uncertainty associated with it. When we say about uncertainty, there are two terms, precision and accuracy. The result would be expected to be precise and accurate. So precision and accuracy are often referred to while we talk about measurement. Now what is precision and what is accuracy? Let's see this example. It's an illustration of accuracy versus precision using a shooting target. Now let's see. The expected result of this shooting is that the bullet should be hit at the center of this target. If the bullet hit at the center of the target, we can say that the shooting is accurate, right? And the shooter has to do 3 or 4 trials, and for all the trials, the person can shoot at the exact place. The bullet will hit at the exact place. If that happens, we will say that it is precise. So in this case, it's accurate and precise. Like we are expecting the bullet to hit at the center, that happens. So the expected result happens, or it is close to the expected result. So it is accurate. And for all the 4 trials, the bullet hit at the same place. That means there is a closeness for all the for the result of for all the 4 trials. Then we can say that it is precise. Now consider this case. Here there is no accuracy. The bullet hits at some other place, so accuracy is not there. We are expecting the bullet to hit at the center, then only it is accurate. That is the expected result, right? The expected result doesn't happen, and it is not close to the expected result. So it is not accurate. But there is closeness for the result. Like for all the 4 trials, the bullet hit at the same place. Exactly almost at the same place. So there is a closeness, right? So we can say that it is precise, but this is not accurate. In this case, we can see that it's little accurate. It's almost close to the expected value. It's somewhat close to the expected value, expected result, but not precise. For all the 4 bullet hits at the different places. So it's not precise but accurate. And the final one, it's not precise or not accurate. Accuracy is also not there and precision is also not there. So if the value of different measurements are close to each other and hence close to the average value, the measurement is said to be precise. See in this scenario, it's precise, it's close to each other. So it's precise. and hence close to the average value. If you take the average value, it's close, so it's precise. The precision refers to closeness of various measurements for same quantity. So when we come back to the chemical experiment, the experiments which we are doing in laboratory, we will be doing different trials for an experiment, and for all the trials the values are similar. We can say that there is a precision, it's precise. Whereas accuracy means there will be a true value, there will be a real value, and we are doing the experiment and we are getting the values which is either same or close to the true value or the correct value or the exact value, then we will say that the measurement is said to be accurate. And accuracy is the agreement of a particular value to the true value of the result. For example, let's say this. For an experiment, the true value is 2.00 gram. This is the correct value or actual value for a result for an experiment. And a student A is doing the same experiment and doing two trials. For the first trial, student A got 1.95 gram, and for the second trial 1.93. These values are precise, means there is a closeness. The actual value is 2.00 gram and the average is 1.940. In this case, the average is not close to the true value, but it's close to each other. The values are close to each other. So we can say that there is a precision but not accuracy. So it's not accurate but it's precise. The result is not accurate but precise. And student B doing the same experiments, repeat the same experiment and obtain 1.94 gram and 2.05 gram. The true value is 2.00 gram. We know why in chemistry experiments, while we are doing the quantitative measurement, all the 0.05 and all the digit matters, right? So this 2.05 and 1.94 are not close to each other. And they are not close to the true value. There is a difference of 0.05 here and it's 1.94. There is a difference with the true value, right? So they are not precise nor accurate. There is no accuracy. It is not close to the true value, or they are not close to each other. Average is not close to each other. So we can say that it's non-accurate and non-precise. The student B's result is non-accurate and non-precise, whereas student A, its precision is there but it's not accurate. Then let's see student C repeat the same experiment what student A and student B have done, and the measurement reports like 2.01 gram and 1.99 gram. The true value is 2.00 gram, so there is a closeness to the true value. 2.01, 2.00, somewhat close. 1.99, 2.00 gram. It's almost close to the actual value. So there is an accuracy. There is an accuracy. And when you see the mean, it's between 2.01 and 1.9 and the average. So we can say that precision is also there. So student C's value is both precise and accurate. Hope the precision and accuracy is clear to you. All the students, student A, B and C have done the same experiment, but they are getting different value. This is because of the errors. The errors either made by them while taking the measurements, by holding the apparatus not properly, or maybe due to many reasons, or either maybe due to the errors in the apparatus itself. They may not be standardized or something like that. You will be learning about errors in coming classes, more detail in coming classes. The uncertainty in the experimental or calculated value is indicated by mentioning the number of significant figures. That's why we are learning significant figures here. So if you are doing a volumetric analysis and we are getting the result as 11.2 milliliter and we are writing it as 11.2 milliliter, in this case the 11 is certain. We are sure that there is 11 is there, and this 0.2 is like uncertain. So the uncertainty would be like plus or minus 1. This is how we will calculate it as plus or minus 1. So to write the uncertainty, to express the uncertainty, we will be mentioning the number of significant figures. That's why we are learning significant figures, and we should learn significant figures for doing the mathematical problems coming in this chapter also. So next is rules for determining this number of significant figures. It's very easy. First one is we have to count all non-zero digits and they are significant. So all the non-zero digits are significant. So there are 3 significant figures in 285 centimeter. Here 0.25 milliliter, there are only 2 significant figures. This 0 will not be considered. Rule number 2, 0 preceding to the first non-zero digits are non-significant. So zeros in front of the first non-zero digits are not significant. 0.003, there is only 1 significant figure, and in 0.0052 there are only 2 significant figures. Even though there are 1, 2, 3, 4, 5 digits, there are only 2 significant figures. So all the zeros in front of a non-zero digits are non-significant. And the third rule is zeros between non-zero digits are significant. So if there are zeros in between 2 non-zero digits, they are significant. So there are 4 significant figures in 2.005. The fourth rule, zeros at the end or right of a number are significant provided they are on the right side of the decimal point. If there is a decimal point on the right side, then the zeros are significant. That the zeros at the end or the right of a number are significant if there is a decimal point. There is no decimal point in 100 grams, so there is only 1 significant figure. In 100 point gram, there are 3 significant figures. 100.0 gram, there are 4 significant figures because there is a decimal at the right side. And for all the objects like book, ball, box, all those things for an objects, while counting the objects, they are all significant figures. You can say 2 balls, 5 balls, 20 books, 30 books, like that. For an object, they are all the numbers are significant figures. And while writing in scientific notation, all the digits, all the coefficients are significant. 4.01. So there are 3 significant figures. So there are total 6 rules for determining the number of significant figures. All non-zero digits are significant, and the zeros in front of the first non-zero digits are not significant. Zeros between the non-zero digits are significant, and zeros at the end or the right side of a number are significant provided they are on the right side of a decimal point. For counting the number of an object having significant figures are significant, and when writing the numbers in significant notation, scientific notation, the coefficient parts are significant. Next is about the mathematical operations using significant figures. While doing the mathematical operation, if it is for addition and subtraction, we have to do the math and check which number is having the least number of significant figures. The final answer has to be rounded up in such a way that it must have the least number of significant figures in which the question is having. See, in this case, the 18.0 is having least number of significant figure. It is having only 3. So the final answer will also be having only 3 significant figures. And there is only 1 digit left after the decimal point. So the final answer will also have only 1 digit after the decimal point. Same is the case of multiplication and division. We have to multiply or divide, and we have to round up the final answer. We have to check if is there any number with the least number of significant figures. The final answer will also have same number of significant figures, and we have to see how many digits are there next to the decimal point. For the least numbers, we can see there are only 1 digit for 2.5, 1 digit after the decimal point, so the final answer will also have only 1 digit. We need to know all the mathematical operations using significant figures for doing the calculation part of your experiment which you are doing in the lab. Hope this video is helpful to you. Next video we will be discussing about the law of chemical combination. See you.